Oi gente, eu sou Rafael Souza e esse é mais um vídeo vinculado à Semana Quântica. E hoje nós temos um convidado muito especial, que é o Byron Freelon, que vem lá dos Estados Unidos para falar um pouco com a gente sobre as suas experiências dentro da mecânica quântica.
My name is Byron Freelon. I'm a professor of physics. I work at the University of Houston, and I am a researcher in condensed matter physics.
Nice. It's a pleasure for us to welcome you. And you have some questions for you about your work.
Okay.
And the first is, many of your recent papers explored 2D magnetic materials like CRSBR. And what are the most extreme quantum aspects of these systems?
Okay. So I study something called 2D magnets or two-dimensional magnets, and the most interesting quantum mechanical aspects of these materials might be the fact that there are many different quantum degrees of freedom that are related or linked. For example, a quantum degree of freedom is the charge of the electron in a material. It's the spin or the magnetic moment or the magnetic spin of electrons in the material. It's the orbital location of electrons in materials or their orbital occupation in the material. And it's also the atomic position or the position of atoms. So those are 4 different quantum degrees of freedom: charge, spin, orbit, and lattice, right? Which are all interconnected in 2D magnets, right? And so the connection of all of those quantum degrees of freedom make understanding the material properties very challenging, because not only are those degrees of freedom connected, but they're delicately connected, very sensitively connected. So if you change let's say the atomic position in some way by introducing, let's say, strain, okay? If you change the atomic position just a little bit, you may find that the magnetic spin, okay, starts to change. So you can even change the magnetic ordering or the magnetic state of some of these 2D magnets. And that's what makes a lot of technological folks and a lot of engineers so interested in 2D magnets. It's the possibility to change the magnetic state by using something like strain or maybe even laser light. And so magnetic states are very important technologically, because, for example, if you take a hard drive or a memory system, we store information by keeping track or organizing the magnetic states and organizing the direction of electron spin. And so if you can change or organize electron spin in some way using strain, lasers, ultra-fast lasers, there's a lot of technological promise to build memory devices, or maybe even devices that work on the conduction of magnetic information rather than charge information. So, for example, silicon chips are based on electronic charge transport and conduction. But in 2D magnetic material, it's might be possible to conduct information or transmit information by moving or causing magnetic spins to change in some way. In other words, conducting magnetic information as opposed to electrical charge information.
Yeah, I understand the quantum physics is very complex, but it have the many advances technologies, yeah.
Yes.
And how can the quantum properties of these materials contribute to developing technologies like spintronics or quantum computing?
Right. So, for example, if you can ask the question, for all of the devices that we've developed based on silicon and semiconductors, right? Are there devices that we can develop using magnetic spin? Silicon semiconductors obviously use electronic charge, and we modulate or we modify something about electronic charge, and that will change the electrical conduction properties in a semiconductor, right? We are now interested in asking, can we modify magnetic ordering? Can we modify, let's say, electron spins and get conduction or get some result that we can use in order to, let's say, convert to a 0 or a 1, right? And so 2D materials are ideal spintronics candidates because, as I said, many 2D magnets, they offer you the opportunity to easily change spin states, right? With, let's say, something like light, in some cases, an external voltage, right? And 2D magnets are also, it turns out that a lot of them allow the transport of magnons, okay, over great distances, like millimeters, right, without the loss of energy, heat energy. So you know that in silicon, when electrical charge conducts or it moves, there's always some loss of energy due to heating, for example. The conduction of magnons is a little different. There could be as much as 1,000 times less energy loss when a magnon conducts. What's a magnon? A magnon is just the change of the direction of an electron spin.
Yeah.
And if I could get that change in spin direction to move or be propagated through a material, that is an example of magnon transport. Turns out that in a lot of 2D materials, magnons transport very smoothly and easily and over great distances, like millimeters. So people are interested in magnon transport and trying to develop it quite a bit. So that would be spintronics, using spin to create information, store information, and to transport information, right? In quantum computing, it's a little different, and I'll just say that in the case of quantum computing, 2D magnets might be used in something you can call quantum interconnects. And I'll try to be very simple about, but a quantum interconnect connects your quantum computing system, which is usually a quantum mechanical system with 2 levels, such that you can change spins states from one to the next. You can create a qubit, hopefully. But typically, those quantum mechanical systems have to be kept very cold, and connecting to those systems, connecting your laboratory equipment to those systems is not trivial, because as soon as you put a wire or connect a wire to your quantum system, you get heating of the system, right? So people are interested in understanding, how can you connect to a quantum system? How can you understand the spin states or qubit states? How can you read and write the qubit spin states without decoherence or without heating up the quantum system? One way is to use radio frequency waves, because radio frequency waves can cause electron spin directions to change. Okay, so you can imagine a 2D material where you have a laser talking to it, and within the 2D magnet, a radio frequency wave is generated, and that radio frequency wave communicates to your quantum computing system, right? So you have kind of like a transducer, a quantum transducer from light waves to radio frequency waves. That's sometimes called a quantum interconnect or a quantum computing interconnect. And they're very important, again, because you have to have a way to communicate with your quantum system without wires, let's say, or without heating them. So that's one big area of interest that people have when they think about 2D magnets and quantum computing.
Understand is the very important, I think, for humanity because the society and they have many opportunities in our study quantum mechanics and the quantum computing.
Yes.
Okay, next, what strategies do you find effective in communicating complex quantum physics concepts to undergrad or high school students?
Okay, so
it's difficult.
Well, yeah, that's a difficult question. It's a very good question. You know, one of the reasons it's difficult is I spend a lot of time communicating with graduate students and not high school students and not undergraduate students, really. And of course, quantum mechanics is difficult anyway, right, by itself. But I have been really interested in diffraction concepts, okay? And I think one way to maybe get high school students or young students prepared to think about quantum mechanics is by diffraction. The two-slit diffraction problem, where you have waves approaching two slits, and then you have a screen on the other side. You can get, when you have two slits and you have light passing through, you don't just simply get two beams of light that show on your screen, right? In some cases you can, but if the slits have the right size, right? If the width of the slits is similar to the wavelength of light, right? Then you'll get diffraction. That's a similar process that people like Einstein and other folks thought about, except they didn't use light, they used electron waves, right? And the two-slit experiment was very helpful in getting Einstein and others to understand that electrons were actually behaving like waves because they were diffracting, right? And so I think getting young students to think about diffraction itself can be a good way to get them to understand quantum mechanics, especially if they start to appreciate the fact that electrons were just behaving in a very weird way. When you send the electron beam into the two different slits, right, you just couldn't explain the result by thinking of the electron as a point particle, right? So I think diffraction would be a good first step, and then talking about electron diffraction and how it suggested that that particles are both wave and that electrons are both waves and particles.
Okay, understand. I think it is possible to teach in quantum physics for high school too, because he have many students have curiosity and research about physics quantum. For me is the incredible for me because I am teacher physics and in my classes I talk about quantum physics and the people have is curiosity and the complexity too, but it's necessary to talk about this.
Yes, well, I love diffraction, so I have my favorites, but so diffraction is a favorite subject for me. But it really is, diffraction really can be important. There's so many simple examples of diffraction, like even with water waves, and you put two openings in a water tank, as we say. But diffraction, also gives so much more information. For example, the structure of the DNA helix came about from diffraction experiments. And so getting students, we've actually started building some toys in my lab for some grants, right? But getting students to diffract from a single string, then two strings, then a string like this, and then a set of strings like this, is a way of getting them to understand how diffraction can give you information about the helix itself, right? There's some steps that need to be taken because diffraction gives you information in what we call momentum space, not real space. Yeah. So diffraction is not real space imaging, right? So there's some complications, but there are some simplistic diffraction experiments that can get students to start understanding very complex ideas. I don't know if that makes sense or not.
Yeah. Okay, the last question is, how do you see the role of interdisciplinarity among physics engineers and the material sciences in training the next generation of quantum scientists?
Yeah. Well, science has always been a multidisciplinary pursuit or multidisciplinary process. And so it will remain a multidisciplinary process. But I think for the next generation, one of the obvious things that will change is the role of computing. The role of computers continues to evolve every day, right?
Yeah.
And so I think computing will continue to tie the different disciplines together, whether or not you're talking about how to more easily interface with your experiments through your cell phone. Okay, that's a simple one. Or whether you're talking about how to develop code that actually visualizes, quantum mechanical processes or quantum mechanical effects. So people have been writing code, for example, that helps students see quantum mechanical ideas, right? However, we now need to write code that helps us visualize what it looks like inside of materials, right? And what a quantum mechanical process or probability might suggest for the properties of a material. So I think computing is going to continue to play a very, very large role in linking the disciplines. Just like I think math, we say math is a common language across engineering, science. Okay, fine. But I think we're going to see that coding is going to become a common thread across the different scientific disciplines. It's getting easier to code too, right? So, I used to ask my students when they started, write me a Python code to do this. Let's learn Python. Now they can go to Google and say to Google, write me a Python code that does this, this, this. So it's very easy. So with the ability to code is getting easier for people. And so what they produce is going to become more and more sophisticated, right?
Yeah.
It's like a pyramid. The base is getting very solid. And so people's creativity is going to generate higher and higher power.
Essa foi a participação do Byron Freelon, que para nós foi uma honra enorme recebê-lo. A sua participação está vinculada ao primeiro workshop de físicos e físicas negros e negros do Brasil, em parceria com os Estados Unidos. Logo mais vocês terão informações de como irá se dar as inscrições e também a data de execução do evento. E a gente só tem a agradecer as parcerias que a gente tem feito. O Instituto Federal da Bahia tem se colocado nesse campo da física quântica em termos de divulgação Divulgação Científica e a Universidade Federal da Paraíba também, trazendo vários pesquisadores de todo o mundo, e para nós é uma honra recebê-los. É isso, até o próximo.